Greetings and welcome once again to Shiny Grades Online School. Today I'll be taking you through Mumias West Sub-County Joint Evaluation Test, Chemistry Paper 1. Please, if you are new to this particular channel, find the time to subscribe to our YouTube channel, Shiny Grades Online School, and as well share this video to reach as many learners as possible. Starting with question number 1. Name two apparatus used for measuring exact volume of liquids. We need to understand that learners in the laboratory, we have several apparatus that are used for measuring volume. Some of them are used for measuring exact volume, and others are used for approximating volumes. One of the apparatus that are used for measuring exact volume include, we have volumetric flask, we have volumetric flask, and we also have a pipette. These are examples of apparatus that can be used to measure exact volume. We may also have a burette that may also be used in measuring exact volumes. We also have other apparatus that are used for measuring approximate volume, and we may have measuring cylinders, we may have beakers for approximating volumes. So learners, for you to score 2 marks, you get to give 2 apparatus, each 1 mark. Moving to the next question, part B. Give a reason why laboratory apparatus are made of glass. In the laboratory, most of the apparatus are made of glass, and the reason as to why most of these apparatus are made of glass, it is 1, they are transparent. So glass is transparent. Glass is transparent, and therefore whoever is doing the experiment will be in a position to make accurate observations. Another reason as to why these apparatus are made of glass is because glass does not react with most of the chemicals. Glass does not react with most of the chemicals. Most of the chemicals. You are only supposed to give 1 reason. Moving to question number 2. State Graham's law of division. Graham's law of division, as explained in Form 3 in gas laws, states that at constant temperature, at constant temperature and pressure, the rate of division of a gas, is inversely proportional to the square root, is inversely proportional to the square root of its density, That is how the Graham's law of division states, and stating it correctly, you were supposed to be awarded 1 mark. Let's move to part B of this question. Gas Q takes 10 seconds to diffuse through a distance of 1/5 of a meter. Another gas R takes the same time to diffuse through a distance of 10 centimeter. If relative molecular mass of gas Q is 16, remember this is not volume, supposed to be is 16. The relative molecular mass is 16. Calculate the molecular mass of R. So here, learners, remember we are given the time taken by gas Q and also the distance covered by gas Q. So we are going to use later the relationships that says the rate of gas Q over the rate of gas R is inversely proportional to the molecular mass of gas R over the molecular mass of gas Q. This is the relationship that we are going to use, learners, and therefore we are supposed to do some calculations here so that we may be in a position to obtain rate of these two gases in gas R and Q. So let's begin by looking at the distances covered by these two gases. We have been taught that gas Q takes 10 seconds to diffuse through a distance of 1/5 of a meter. So we are going to calculate the distance covered by gas Q. So this gas, we are told that it covered 1/5 of a meter, and we know a meter is equivalent to 100 centimeters, and therefore here we are going to get 20 centimeter. Now that we have the distance that gas Q covered, and we were also told the distance that gas R covered. Gas R, distance covered by gas R, it is 10 centimeter. So it is 10 centimeter. So we begin now by looking at rate of these two gases. So I begin by looking at the rate of gas Q. The rate of gas Q, rate is given by distance over time, and the distance covered by gas Q is 20, and I divide by the time that it took, 10 seconds. So here I'm getting 2 centimeters per second. That is the rate of gas Q. Then looking at the rate of gas R, I'm going to have 10 centimeters divided by, we also told that another gas R takes the same time, so it's going to take again 10 seconds. So in this case, I'm going to have 1 centimeter per second. 1 centimeter per second. So in this, I can now, using the relationship, find we have been taught to find the relative molecular mass of gas R, and therefore I'll use the equation and I'll substitute. So the rate of gas Q is, according to our equation here, we have, according to our equation, rate of gas Q is 2 centimeter over rate of R is 1, is equivalent to the relative molecular mass of R, which is 1, divided by the relative molecular mass of Q, which is 16. We have been told it is 16. So in this case, I'm going to square both sides. I apply the knowledge of mathematics here. I square both sides so that I remove the square root. When I square both sides, I'm going to have 4 is equals to, remember this is molecular mass, it's supposed to be molecular mass of gas R. So I'm going to have molecular mass of gas R over 16. And when I work this out by doing cross multiplication, the molecular mass of gas R is going to be 16 multiply by 4. And when we work out this, we obtain 64. Remember, relative mass has no units. And by working out this, you'll be able to score 2 marks. Working out this distance, you get half a mark. And then working out the rate, half a mark. This rate, half a mark. And getting the answer here, you'll be able to be awarded again half a mark. So this is how we were supposed to work out this question. The relationship between rate and molecular mass is what we were to use to work out this question. Let's move to the next question. Starting with copper 2 oxide, describe how crystals of copper 2 carbonate can be prepared in the laboratory. So take note of this typing error. So how do we prepare as crystals of copper 2 carbonate? By starting with copper 2 oxide. So learners, this is salt preparation in form 2. So we begin by saying that we add excess copper 2 oxide, add excess copper 2 oxide to dilute sulfuric 6 acid, to dilute sulfuric 6 acid, then filter to obtain or to remove excess copper 2 oxide, to the filtrate, add sodium carbonate, remember in form of a solution, add sodium carbonate, then filter to obtain copper 2 carbonate as residue, copper 2 carbonate as residue. Then after you have obtained the residue, wash the residue and dry in between filter papers. Wash the residue and dry in between filter papers. This is how we were supposed to prepare. Remember, we add excess copper 2 oxide to dilute sulfuric 6 acid, that is to prepare a solution of copper sulfate, and then from there we filter to remove excess copper oxide that has not reacted, and then we filter to obtain sodium. We add to the filtrate, we add sodium carbonate, and then after they have reacted, we filter because there is precipitation occurring to obtain copper 2 carbonate as residue, and then we wash and dry it in between filter papers. The distribution of the marks, the moment you say we add excess of copper 2 oxide to sulfuric, we'll award you half a mark, and then after filtering, half a mark, and again to the filtrate adding sodium carbonate, half a mark, and then obtaining copper 2 carbonate, half a mark, and then washing and drying in between filter papers, half a mark. And we also have obtaining copper 2 carbonate residue, and it is going to give you a total of 3 marks. Question number 4. Draw and name an isomer of butane. Draw and name an isomer of butane. You know butane is an alkane, and the first isomer of butane is butane itself with the straight chain of butane with 4 carbons. But here we are going to have now the second isomer of butane. So we may have C, C, C. We draw an open chain like this, or we compress the methyl. We have it this way. Then the methyl, we compress it this way. Then we have the hydrogens on the sides. And because we have been taught to draw and name the isomer, we have a straight chain as having 3 carbons, and then the methyl being attached on the second carbon. So we are going to have 2 methyl propane, 2 methyl propane, and this gives you 1 mark. Drawing have a mark and naming have a mark. Let's move to the next question. Describe how to distinguish between ethane and ethene. Supposed to be ethane and ethene. So how do we differentiate between an alkane and an alkene? Here we can use an oxidizing agent, and the commonly used oxidizing agent is acidified potassium manganate 7 that changes or decolorizes in alkenes, which is not the case in alkanes. So how do we describe how to distinguish between the two? So we have 2 methods. One is by carrying out combustion, and again by using a strong oxidizing agent. So we have 2 options here. One, by carrying out combustion, here we explain by saying that ethane burns with blue flame. Ethane burns with a blue flame, while ethene burns with a sooty yellow flame, or a yellow sooty flame. That is one way to distinguish between the two. So this one is enough to give you 2 marks. Or you say you use the chemical that we said a strong oxidizing agent. So by use of oxidizing agent, acidified potassium manganate 7, whereby ethene decolorizes while ethane does not. So you can still use that to describe or to distinguish between ethane, which is an alkane, and ethene, which is an alkene. Let's move to the next question. Use the bond energies below to determine the enthalpy change for the reaction below. We have been given an equation between hydrogen and chlorine to obtain hydrogen chloride gas. So how do we determine the enthalpy change for the reaction? How do we determine the enthalpy change for the reaction? We begin by rewriting this particular equation by opening the bonds. We have hydrogen bond plus chlorine bond, and we obtain two hydrogen chloride bond. Remember, learners, that this is the side of bond breaking. That is on the reactant side, and this is the side of bond formation on the product side. This information is important because we know bond breaking is an endothermic reaction and bond formation is an exothermic reaction. So because we have been given the bond energies, we are going to work out this bond breaking energy and bond formation energies, and then we are going to determine the difference between the two, and then we are going to get the enthalpy change. So we are going to begin with bond formation, bond breaking. Bond breaking, it's between hydrogen bond, and we also have chlorine bond. So in this case, because it's not balanced with any number, we are going to have positive 346 plus positive 244, and then this gives us the energy on the bond formation side, which is 2. It is between hydrogen chloride, so it's 2 into positive 432. So when we do the summation, we are going to have positive 590, and this is going to give us positive 864. So we need to understand that enthalpy change is given by bond breaking plus bond formation. Now, we need to understand that bond breaking is an endothermic and bond formation is an exothermic reaction. So on the side of bond formation, we have to include a negative sign so that we do the summation. So we are going to have positive 590 plus negative 864. So working out this, we are going to have negative 274 kilojoules per mole. Remember, our bond energies are also in kilojoules per mole, so we're going to give it again in kilojoules per mole. So this gives you a total of 2 marks. Let's move to the next question. Define molar enthalpy of formation. Define molar enthalpy of formation. This is a Form 4 question. Again, molar enthalpy of formation, and understand that in Form 4 you have learned several types of enthalpies, one of them being the enthalpy of formation. So the enthalpy of formation, we define it as the enthalpy change is the enthalpy change that occurs when one mole of a substance is formed from its constituent elements. Substance is formed from its constituent elements. So, for instance, if I have something like methane, for me to form methane, I know I need carbon and hydrogen. So the energy change that is required at this point to form methane is the enthalpy of formation methane. So that kind of energy that leads to formation of 1 mole of methane, that kind of enthalpy change is what we call molar enthalpy of formation. Let's move to the next question. Question number 6. The following setup apparatus is used to prepare and collect oxygen gas. And have a look on the setup. We have a round bottomed flask. We have a dropping funnel. We have reagent, which is substance P, and hydrogen peroxide. And you can see that this is one of the methods of preparing oxygen. Remember, we have other methods of preparing oxygen in the laboratory, like by adding water to sodium peroxide. We may also have thermal decomposition of potassium nitrate, and we also have thermal decomposition of potassium manganate 7 that also gives us oxygen. So let's focus on the question that we have on board. Name and state the role of substance P. Substance P, we know this method. We have said that we have several methods of preparing oxygen. Methods of preparing oxygen. One, I've said, is the one that we use hydrogen peroxide and another substance, that is the substance P that we have been asked here. And in this case, we always use a catalyst that we call manganese for oxide. So here, we don't add it. Remember, it's just a condition. So manganese for oxide. That is one way of preparing oxygen. Another way of preparing oxygen is by reacting sodium peroxide with water. And another method is by decomposing potassium nitrate. And we may also have the same decomposition of potassium manganate 7. So these are methods of preparing oxygen. And we are focusing on the first one, which is reacting hydrogen peroxide with in presence of a catalyst, which is manganese for oxide. So substance P is manganese for oxide. Manganese for oxide. That is the name. We are taught to name and state the role. The role of this is the name. And the role is, it's a catalyst. Is a catalyst. Or you can say it catalyzes the reaction. It catalyzes the reaction that leads to formation of oxygen. So stating the name, have a mark, and stating the role, have a mark. So means that it is oxygen gas. It is oxygen gas. Moving to part B of this question, write an equation for the composition of hydrogen peroxide. So I've said that here we need hydrogen peroxide. Remember, at this stage you're supposed to be writing chemical equations, not word equations. I decompose this in presence of manganese for oxide, and I obtain water and 2 molecules of water and the oxygen there. Remember, I've balanced before balancing the peroxide, but because we have 2 oxygens here and on the other side we have 3 oxygens, so I have to put a 2 on water, so that now I also put a 2 on peroxide to obtain 4 oxygens and 4 hydrogens, and this gives you a full mark. That's why you're supposed to write the equation. Give uses, one use of oxygen. We have several uses of oxygen. Oxygen is used in hospitals. So we have air enriched with oxygen is used in hospitals by patients with breathing difficulties. So we have air enriched with oxygen is used in hospitals by people or patients with breathing difficulties. We may also have another use that oxygen when mixed with helium may be used by mountain climbers and deep sea divers. Oxygen, a mixture, that is a mixture of helium and oxygen. Oxygen when mixed with helium is used by mountain climbers, and also used by deep sea divers. You can also talk of oxygen being used to burn gases such as those for propelling rockets. We may also talk of during steel making, oxygen is used to remove impurities, and many other uses of oxygen that you learned in Form 1. So those are some. You are supposed to only give one use of oxygen for you to score 1 mark. Please let us note that as much as you study any preparation of any gas or any substance, the use is more important because more of application where you're going to apply it in life. So uses of this substance that you do prepare is very important to get to know them. So let's now move to next question, question number 7. A self-rising baking flour contains a mixture of tartaric acid and sodium hydrogen carbonate. State and explain the role of tartaric acid in the mixture. So when you look at this, it's an acid. Let's not be confused by this name. And we have sodium hydrogen carbonate. So how does the flour mixture rise? How does this baking flour rise? What happens? What is the science inside that particular activity? So we state and explain the role of tartaric acid in the mixture. So what happens? This particular acid reacts with the carbonate to produce a gas which is carbon dioxide gas, and this gas is the one that makes the dough to rise. So here we say the role of this acid, it reacts with sodium hydrogen carbonate in that we are given here. So we say the role is it reacts with sodium hydrogen carbonate to produce carbon dioxide, which rises the dough. Stating this gives you 1 mark. So that is the science behind rising of the dough. Question number 8. Define the term half-life. Here is radioactivity. Define the term half-life. How does it state? Half-life, as defined in Form 4 radioactivity, is the time taken for a radioisotope for a radioisotope to decay to half its original mass, to decay to half its original mass, So stating this, it was supposed to give you a whole mark. That's how we define half-life. Part B of this particular question: a certain nuclide has a half-life of 2.5 hours. I want you to take note of that. A certain nuclide has a half-life of 2.5 hours. What percentage of a given mass of the nuclide, would be left after 7.5 hours? So the half-life is 2.5 hours and we are given a period of 7.5 hours. So here, for us to get the percentage, we need to know the number of half-lives. So here, we are going to begin by looking at number of half-lives. The number of half-lives that we have, we are going to take the total number of times that we are given, 7 hours, and we divide by 2.5 hours, which is the half-life, and here we are going to get 3 half-lives. So we have only 3 half-lives, and because we have been taught what percentage, because we understand that percentage will never be out of 1,000, percentage is always out of 100. So because we have 3 half-lives, then from 100, the first half-life itatupeleka, it is going to give us 50%. Then the second one is going to give us 25, and then the third one is going to give us the half of 25, which is 12.5. So remember, this is the first half-life, this is the second half-life, and this is the third half-life. And that's the reason we began by looking at the number of half-lives, and this gives us 2 marks. We may also have an alternative method, which we use a formula that remaining amount is given by 1/2 or half power n multiplied by the original amount. N, in our case here, is the number of half-lives. Take note of that. So RA means remaining amount and OA means original amount. So here we have already been given the original amount, which is 100%, because percentage is not always out of 100. So we are going to look at the remaining amount in terms of percentage. Remaining amount is equals to 1/2 power 3. So in this case, I enclose with 3 and I multiply by the original amount, which is 100. So when I look at this in different perspective, I can convert 0.5 into 0.5. So it's going to have 0.5 power 3 multiplied by 100. When I work out this, I'm going to get 0.12. I multiply by this 100. 0.125 actually. I multiply by 100, and here I'm going to obtain 12.5, and this is a percentage because we were working with percentage. So still you're going to get the answer. So you had an option of using this method or using this method. Again, you are to get 2 marks. You are to get 2 marks. So just an alternative method, and all of them will lead you to the correct answer. So I want us to move to the next question. The following diagram shows the setup they are used in the electrolysis of molten copper 2 chloride using inert electrodes. These inert electrodes. So you can look at it and you can notice a mistake, because we have the shorter terminal representing the anode, and this one, the longer one representing the cathode. And we have been taught that when the longer one should represent the anode and the shorter one should represent the cathode. So let's now dive into this question. Looking at it, the first question says, name a suitable pair of electrodes that can be used in this experiment. So we have been told that they were using inert electrodes, and one of the inert electrodes that we use during electrolysis is carbon electrode or graphite. So we may use carbon electrode or electrodes. And another one that we may use is platinum electrodes. Platinum, which are also inert. Platinum electrodes. They don't react, they don't take part, or they do not react with most of the electrolytes that are used. So these are inert electrodes that are used. So we have this each giving you supposed to be name a suitable pair. So it's supposed to be 1 mark when you name carbon electrode or platinum electrodes each. Only one was to give you 1 mark. Let's move to the next question. Identify the anode and the cathode. So we look at the diagram that we have. We identify the anode and the cathode. Remember, learners, that anode is the positive terminal, or is the electrode connected to the positive terminal. Cathode is the electrode connected to the negative terminal. And I say that one way of identifying the cathode is when you realize that it is the terminals is shorter. It is shorter. This one is always long. So in this case, we can look at this and we conclude it the anode. And this, because it's short, we conclude is the cathode. Sometimes they are not labeled, so you'll be required to label them on the diagram. So in our case here, we are taught to identify the anode and the cathode. So what we are supposed to do, because they have letters, we look at the electrodes. These are the terminals and these are the electrodes. So electrode C is the anode, while electrode D is the cathode. So here we have C, which is C is our anode, which is the positive terminal connected to the positive terminal, and we have D, which is the cathode, connected, the electrode connected to the negative terminal. So this was supposed to give you half a mark in each case. Part C of this question, write the equation for the reaction at the anode. We need to understand that at the anode, learners, this is where oxidation takes place. We need to understand that we were given our molten copper 2 chloride. Copper 2 chloride, molten, when it is subjected to electric current, it dissociates and discharges copper 2 ions. Remember, this is a binary electrolyte, and chloride ions, which is also aqueous. In this case, the chloride ions are going to be attracted to the positive terminal, which is the anode, and the copper 2 ions are going to be attracted to the cathode, which is the negative terminal. So we have the cathode, copper ions attracted to the cathode, and chloride ions attracted to the anode. So in this case, automatically we are to write an equation at the anode. We are going to focus with the chloride ions. Chloride ions, they are going to move to the anode, and at the anode, that is where oxidation occurs. So in this case, we begin with chloride ions, which are going to be oxidized. In this case, we are going to have chloride ions losing electrons, and we lose electrons by putting an arrow. So the electrons move to the other side. That is oxidation. So for anode, we have said it is oxidation. So in this case, chloride ions loses an electron, and we obtain the molecule of chlorine gas. Then we discharge an electron. One electron is lost. And because we have two chlorines here, molecules, we balance here with 2, and we also balance because -2 means that 2 electrons has been lost, so we also balance with 2 here, and that is the equation at the anode, and this gives you 1 mark. If at any given point you have been told to write the equation at the cathode, this means that copper 2 ions are going to move to the cathode. So copper 2 ions are going to be oxidized, are going to be reduced. At the cathode, there is a reduction that occurs there. So at the cathode, we have copper 2 ions gaining the 2 electrons that has been lost on the side of anode. And here we're going to reduce copper 2 ions to copper metal. And this is going to be the equation at the cathode. So copper is going to gain electrons. When you find 2 positive, it means that according to the periodic table there, we say that when an atom acquires a positive charge, it means that it reacted by losing electrons. So here, if it lost electrons, in this case, we are now making it gain the electrons, the 2 electrons. So anytime you are using a positive ion, never use a arrow like in the case of chlorine. So you're supposed just to add electrons because initially it had lost. So it is 2 positive plus 2 electrons that had lost. So you link this information to that of the periodic table, and then you obtain copper solid. And through that, you're going to have to score. If the question was right at the cathode, anode, that's how you're supposed to do it. So the correct equation was chloride ions losing 2 electrons to obtain chloride or chlorine molecule, and 2 electrons are lost, and we balance with 2, and that's how we obtain the 2 electrons. And actually, when you are writing equations, we start by the side which loses. So we start with the anode, and then the other equation we write is on the cathode. So we start by losing and then gaining. So anytime you are writing the 2 of them, you start with anode, and then you move to the cathode. Through this, you're going to know at the cathode or anode we lost 2. So on the cathode, then we also have to gain 2 electrons because the number of electrons lost should be equal to the number of electrons that has been gained on the cathode. Let's move to the next question. Question number 10. Below is a section of the periodic table. Explain the following observation. The assumption is that this is extracted from period 3 of the periodic table. So the assumption is this has been extracted from period 3. So take note of that. So we have A, B, C, D, E, F, G, H. So explain the following observation. The atomic radius decreases across a period. Atomic radius decreases across a period. So why does the atomic radius decrease across a period? So if I was to use period 3, then I put 11 protons, 12 protons, 13 protons, 14 protons, 15 protons, 16, 17, and 18. When you look at the protons that we have, you realize that this being sodium, for instance, it is 281, and the last one is 288. As you move from sodium to argon, you notice that the number of protons are increasing. So the reason as to why the atomic radius decreases, it is because as the number of protons increases, the nuclear charge also increases. And as the nuclear charge increases, the nuclear charge is more positive, it becomes more positive, and the remaining electrons on the energy levels of the outermost or other energy levels, those electrons are highly or strongly held by that nucleus because it becomes more positive, and that makes the atomic radius to decrease, and therefore we say it is due to the increase in nuclear charge across the period. You may add because of increase in the number of protons across the period. You may add that, but we say due to increase in nuclear charge across the period. due to increase in nuclear charge across the period. This gives you 1 mark. I've said you may add and say because of increase in the number of protons, which leads to the increase in the nuclear charge across the period. B, melting point of E is very low compared to that of D. Looking at E and D, we are told that the melting point of E is very low compared to that of D. E, learners, is phosphorus according to that period, and D is silicon. Silicon, the molecules in silicon are held by strong covalent bonds, the atoms, but in phosphorus they are held by weak van der Waals forces of attraction. So we say E has weak van der Waals forces of attraction. E has weak van der Waals forces of attraction, which require less heat energy, than the covalent bonds of D. So explaining this again, you are to score 1 mark. Part C of this question, explain the difference in electrical conductivity in B and D. Looking at B and D, B probably is magnesium, and D on the other side is silicon. So explain the difference in electrical conductivity of B and D. We know B, being a metal, has delocalized electrons, unlike in silicon, so it does not have delocalized electrons. So we say B is a conductor while D is not a conductor. So we say B is a good conductor while D is a poor conductor. Of course, of electricity. Reason that you are going to give, it's because B has the localized electrons which are not present in D. B has the localized electrons which are not present in D. This again gives you 1 mark. Stating 1 half a mark, explaining half a mark. Moving to the next question, number 11. Bismuth chloride undergoes electrolysis in water, resulting in the equilibrium. We can see bismuth chloride reacting with water to obtain bismuth hypochlorite and hydrochloric acid with a discharge of negative the discharge of 83 kilojoules per mole of heat energy. So we begin by defining or stating what is equilibrium. Equilibrium is a state of balance where the rate of forward reaction is equal to the rate of backward reaction. So is a state of balance, is a state of balance where the rate of forward reaction is equal to the rate of backward reaction. That is what we refer to equilibrium. This gives you 1 mark. Part B of this question: what is the effect of adding hydrochloric acid to the above equilibrium? As you can see, we already have hydrochloric acid here, and we are going to answer this question based on the Leach-Atterius principle that states that when a change in condition is applied to a system that is at equilibrium, the system moves so as to oppose that particular change. So if I was to add hydrochloric acid here, it means that our system is this reaction here. Our system is going to shift to the side which reduces the hydrochloric acid. So I try to add more hydrochloric acid, it moves to the side which tries to reduce that hydrochloric acid. So of course it's going to move to the side which tries to break that hydrochloric acid down to something else. So of course this reaction will shift backwards. So we are going to say the equilibrium will shift to the left, or we can say the equilibrium will shift backwards, or we can say backward reaction is favored. And therefore, this is well explained by the Leach-Atterius principle. So in this case, we can say the equilibrium will shift to the left. The equilibrium will shift to the left. The equilibrium will shift to the left. Or you can say backward reaction is favored. So that is what you're supposed. That is the effect of adding hydrochloric acid to the above reaction. That is to the above equilibrium, not a reaction. What is the effect of increase in temperature on the rate of reaction? So if it was equilibrium, then we could have looked again at the same, because this reaction is exothermic. This represents this symbol here, or this sign represents the forward reaction. But now, what is the effect of increase in temperature on the rate of reaction? Just a normal reaction. So, what is the effect of increasing temperature on the rate of a reaction? The effect is increasing temperature increases the kinetic energy. So we say increase in temperature increases the rate of reaction by decreasing the kinetic energy of the molecules. So we say increase in temperature increases the rate of reaction. Then we add and say by increasing the kinetic energy, of the molecules. And when the kinetic energy of the molecules increased, the number of successful collisions is going also to increase. So this increases the number of successful collisions. This increases the number of successful collisions. Remember, the more we have more number of successful collisions, the more we have more product being formed, and that means that the rate of reaction is taking place at a very fast rate. So let's now move to the next question. Question number 12. The structure below represents a portion of a polymer. This is one of the polymers that are formed by addition, polymerization. And I want to correct it a bit. Because this one has been interfered with by the system. So we have carbon. We have 6 carbons. So I want to retype it, or I want to reconstruct it. That is methyl. This is hydrogen. Another methyl. Hydrogen. Another methyl. Hydrogen at that point. Then we have COOCH3. Then we have H. Then we have this again repeating itself. Then we have H. We have this repeating itself, and we have H. And then we have this, and it is a polymer. It is a polymer. Now, this being a polymer, it may be repeated as many times as possible. We have been taught to draw and name the monomer. What is the monomer? The monomer, as you can see the repeated parts. You can see the repeated parts. You can see this repeats itself again at this point here. So we can extract the monomer. Our monomer is going to be C double bond C. Then we have the CH3. We have the hydrogen at this point. We have another hydrogen at this point. And then we have the COOCH3. So this is the monomer. The name of this monomer is 2-methyl propanoate. 2-methyl propanoate. Supposed to be 2-methyl propanoate. 2-methyl propanoate. We also call it methaclyrate. We also call it methaclyrate. Methaclyrate. That is another name. So that is the monomer of this particular polymer. So I want you to rewrite it to this, and then you look at it. State one commercial use of the polymer. I've said it is 2-methyl propanoate, and one of the use of this particular polymer that we have just looked at. One of the uses, it is used in making window panes, used in making windows. So it looks like it is a clear material, so it can be used in making window panes. So we have used in making windows. We also use it to manufacture dental crowns. Used to manufacture dental crowns. Used to manufacture dental crowns. I want us to move to the next question, question 13. The setup below was used to prepare nitric 5 acid in the laboratory, and you can see this is the setup that is used to prepare nitric 5 acid. You can see fumes of nitric 5 acid, concentrated sulfuric 6 acid is there, and you have the nitric acid being collected on the other side. So the first question is, all apparatus used during preparation of nitric 5 acid are made of glass. Give a reason. So the reason as to why these apparatus are made of glass is because glass do not corrode. So it is to prevent corrosion by the acid formed. So we say to prevent corrosion, by the acid formed. To prevent corrosion by the acid formed. Name solid R. Learners, when we are preparing nitric 5 acid, we use a salt, which is, and in our case, the salt that we usually use is potassium nitrate. Potassium nitrate is commonly used because it do not contain water of crystallization. You may be told to give a reason. So we are told to name, not to give a simple or the formula. So we are going to name it potassium nitrate. Potassium nitrate. Potassium nitrate. Don't give a formula, just name, and this gives you a mark. I've said the reason as to why we use potassium nitrate and not another nitrate is because potassium nitrate, it does not contain water of crystallization like the other nitrates do. Give a reason why it is possible to separate nitric 5 acid from sulfuric 6 acid used as one of the reagents. So the reason as to why we can separate the two, because we are forming nitric 5 acid and at the same time we are using concentrated sulfuric 6 acid. Why is it possible to do the separation? It is because nitric 5 acid is highly volatile. It's like highly volatile. Remember, sulfuric 6 acid is less volatile. So, and again, it has a relatively lower boiling point than sulfuric 6 acid. So we say nitric 5 acid is highly volatile and has a relatively low boiling point than sulfuric 6 acid. Give one of the uses of nitric 5 acid. Nitric 5 acid has several uses. One of the uses, it's used in manufacture of nitrate fertilizers. Used in the manufacture of nitrate fertilizers. Another use, it is used in manufacture of explosives. Used in the manufacture of explosives. We have several questions that you may get from this question. You may be taught to explain why the acid collected or prepared is yellow in color, and this because of the presence of dissolved nitrogen oxide that is also due to the decomposition of nitric 5 acid. You may also be told to explain why the fumes are brown. The fumes of nitric 5 acid are brown, they are always red-brown in color. And this is due to the nitrogen oxide that is formed due to thermal decomposition again of nitric 5 acid. And you also may get another question that says you explain why an acid salt is formed, because when we are preparing this particular acid, we react potassium nitrate with sulfuric 6 acid, and when we react this, we always obtain an acidic salt, which is potassium hydrogen sulfate. We also obtain the acid nitric 5 acid. So this salt here is an acidic salt. We do not obtain potassium sulfate, which is a normal salt. So why do we obtain an acid salt and not a normal salt? The reason is because to form a normal salt, it requires high temperatures that cannot be achieved in a classroom or in school laboratories. So it requires a lot of temperature, a very high temperature. So to prepare a normal salt or to obtain a normal salt, it requires a lot of temperature or very high temperatures. So let's now move to question number 14. Let's now move to question number 14. Question number 14. Distinguish between covalent and additive bond. We need to understand that covalent bond is a type of bond that involves two atoms, each contributing to the shared pair of electrons, while for the additive bond is a type of bond where the shared pair of electron is contributed by only one atom. So we write and say covalent bond involves two atoms contributing to the shared pair of electrons, while additive bond is formed when the shared pair of electrons is contributed by one atom. So giving this statement correctly, you are supposed to be awarded 2 marks. Let's now move to question number 15. The following diagram represents part of a large-scale manufacture of hydrochloric acid plant. When you look at it, you can see the setup. We have a gas B passing into the combustion chamber, and a gas A, the arrow should be pointing through the jet. The gas A that is passed through a jet. Then we have production of hydrochloric acid. We have presence of glass beads in the absorption column. Then we have water that is coming from the top. This is the setup that is used during the manufacture of hydrochloric acid in a large-scale plant. And as you all know, in the manufacture of hydrochloric acid, we have two main raw materials. And these two raw materials, we have hydrogen and chlorine. We have hydrogen gas, and we also have chlorine gas, which are the main raw materials. We need to understand that during the process, hydrogen and chlorine, they are bound to form hydrogen chloride gas. They are bound together in the combustion chamber to form hydrogen chloride gas. To prepare hydrogen chloride gas, we need also to understand that these two gases, they are reacted, one of the gases being passed in excess and the other gas being passed in small amount, that is through a jet. So in this, we need to understand that the small amount of the gas used is for hydrogen gas. Hydrogen gas is passed through a jet to react with excess chlorine gas. And this is because these two gases, a mixture of these two gases reacts explosively when heated, and that's the reason we react hydrogen gas with excess small amount of hydrogen gas with excess chlorine gas, because the two gases react explosively when heated. So we also have the presence of water that now hydrolyzes the hydrogen chloride gas to form aqueous hydrochloric acid. Glass beads is there to increase the surface area in which hydrogen chloride dissolves in water. So we begin by now answering the question. Name gases A and B. So gas A, because it's now is being passed in excess, and gas A, which is passed through a jet. Let's begin with gas A, which is passed through a jet, is hydrogen gas. Gas A is hydrogen gas. Gas B, which is now passed in excess, is chlorine gas. Each of these was 1 mark, each have a mark. State the role of glass beads in the plant. The role of glass beads, I've just said, increases the surface area over which the gas dissolves in water. Increases the surface area over which hydrogen chloride gas dissolves in water. Dissolves in water. Let's look at part B of the question. Why is gas A introduced into the reaction chamber through a jet? And we write and say a mixture of chlorine and hydrogen gas, a mixture of chlorine and hydrogen gas, a mixture of chlorine and hydrogen gas reacts explosively. And hence little amount of hydrogen is allowed to react. And hence little amount of hydrogen gas is allowed to react. Is allowed to react. Let's now move to question number 16. The empirical formula of a hydrocarbon is C2H3. The hydrocarbon has a relative molecular mass of 54. Given that the relative atomic mass of carbon is 12 and the relative molecular mass or atomic mass of hydrogen is 1, determine the molecular formula of the hydrocarbon. We know when given the empirical formula shows the simplest whole number ratio in which atoms are found in a particular compound. And the molecular formula shows the actual number of atoms. So in this case, when we are given the relative molecular mass, we can easily determine the relative molecular formula, whereby we say use the formula C2H3 in bracket N is equivalent to the molecular mass, relative molecular mass. This is to determine the number of atoms of this particular compound. So given that carbon is 12, then we are going to have carbon 12 times 2, 2 atoms, plus 1 for hydrogen times 3, there are 3 atoms, into bracket N is equals to 54. When you work it out, you are going to have 24 plus 3 into N is equivalent to 54. 27N is equals to 54. N is equals to 2. So if N is equals to 2, then the relative molecular formula or the molecular formula of the hydrocarbon, now because we have the N that was unknown, we are going to have C2H3 into N. Our N in this case is 2. So our molecular formula will be C4H6. So we have already determined the formula, and that is 1 mark. Draw two structural formula of the hydrocarbon. So learners, we need to understand that with this, we can notice that C4H6 lies in the group of hydrocarbon that we call alkynes. Alkynes because it follows the general formula CnH2n-2, and this is for alkynes. So if this is for alkynes, then I want to have 2 structures for this particular compound. So the first one, I may decide to place the triple bond on the first between the first and the second carbon. Then we are going to have hydrogens distributed at B as follows. We have hydrogen, hydrogen, hydrogen. So we need 6 hydrogens. So you notice that at this point, remember the carbons are supposed to be 4. So we have another carbon at this point. So we have hydrogen, hydrogen, hydrogen. And lastly, we have a nitrogen at this point. So that is the first structural formula of the hydrocarbon. And we may also have another one where we place the triple bond between the two carbons in this way. This way. Then we have hydrogen, then hydrogen, 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 and then again we are trying to forget the carbons are supposed to be 4. So we have hydrogen, hydrogen, hydrogen. That is the second structural formula of the hydrocarbon. Let's now move to part C of this question. Part C of this question. If the hydrocarbon is bubbled through acidified potassium manganate 7 solution, state the observation made. Learners, we need to understand that this particular hydrocarbon that we have just noticed or that we have just identified up here, it's supposed to be an alkyne. And this being an alkyne, because of the presence of the triple bond, we say it is a saturated. It is a saturated hydrocarbon, and it's supposed to change or decolorize acidified potassium manganate 7 solution. So the observation that is going to be made at this point, we are going to say purple acidified potassium manganate 7 solution will be decolorized. Purple acidified potassium manganate 7 will be decolorized. That gives you 1. Question number 17. The following setup illustrates one of the several techniques for separating mixtures. So you can see the setup, you can see mixture M, you can see source of heat at this point. Then we have poured water here that probably is going to pull vapor and change it to a liquid form. So we are being told that name the method of separation illustrated by the diagram. So this type of separation is, we call it simple distillation. It's different from fractional distillation because there is no presence of the Liebig condenser. It's not there, or the fractionating column. So in this case, this is simple distillation. So we say simple distillation. Simple distillation. State the possible nature of mixture M. So when you look at this method, it's a method that we say is done for soluble solid liquid mixture. So this will probably it's a soluble solid liquid mixture. Soluble solid liquid mixture. That is the nature of this particular mixture. Moving to the next question. Name an application of the method of separation illustrated by the diagram. So where do we apply this knowledge? This knowledge can be applied in extraction of sodium chloride from seawater, extraction of sodium chloride from seawater. You can still apply this method in purification of water. Purification of water. That was to earn you 1 mark. You are only supposed to give 1 application. Let's move to the next question. In the equation below, identify the reaction that acts as an acid. The reactant. Identify the reactant. Supposed to be a reactant that acts as an acid, and give a reason for your choice. So in this case, we have a few theories that I try to explain or to define an acid and a base, and one of them is the Arrhenius theory. We have the Bronsted-Lowry theory, and we also have the Lewis theory. And in this case, we are going to define an acid based on the Bronsted-Lowry theory that states that acid is a proton donor. So in this case, we are going to define acid as a proton donor. And a base, we are going to define it as a proton acceptor. A proton acceptor. So, looking at the ammonium ion and water here, you realize that we have lost a proton from the ammonium. Hydrogen, which is a proton, hydrogen has been lost from hydrogen atom has been lost to water. So we have lost a proton. So acid has donated a proton to water molecule. And in this case, we can easily say ammonium ion is the acid, and we give a reason because it donates a proton to water. It donates a proton to, in this case, our proton is hydrogen atom to water. Stating 1 mark and giving a reason 1 mark. Water, on the other hand, it acts as a base because it's a proton acceptor. It's a proton acceptor. Let's now move to question number 19. Element has 2 other isotopes. When you look at this question, it's incomplete. There's a part that has been omitted. Therefore, we are not going to answer this question because there's a part that's not there. We are going to skip and move to question number 20. When a dry cell is discharging, that is in use, the following reaction occurs in the cell. We have zinc reacting with ammonium ion in presence of manganese 4 oxide as catalyst to obtain zinc 2 ions, ammonia gas, and water. That is when it is in use. Given that zinc ions, they have equation for this particular dry cell. We have zinc ions gaining 2 electrons to obtain zinc solid. That is a reduction process with EMF of negative 0.76 volts. And we have ammonium ion gaining 2 electrons again to obtain ammonia gas and water with EMF of positive 0.74 volts. We need to understand that this is electrochemistry, and in the application for the dry cell, how it is used. We know how it looks like, what dry cell looks like, what it has inside it, presence of the carbon rod, which acts as the positive terminal, the presence of zinc can, which acts as the negative terminal, and we also have the presence of powdered carbon, and which is a mixture of, with manganese oxide, and also have a paste of ammonium chloride and zinc chloride that is also found in the dry cell called the leach cell. So this particular cell has been in use in this particular question. So we first calculate the EMF of the cell. What is the calculate the EMF of the cell? How do we work out the EMF? So EMF is given by E reduction minus E oxidation. What does this mean? E reduction means the cell that undergoes a reduction, and the cell that undergoes reduction is the cell that has a more positive EMF value. So this is the cell that undergoes a reduction. It's a cell that undergoes a reduction and it is more positive. And of course, the other side we have the cell that undergoes oxidation and it has a less positive or more negative EMF value. So how do we do it? We're going to have positive 0.74 volts minus 0.76 volts. Mathematically, a negative multiplied by a negative becomes a positive. So we're going to have positive 0.74 plus 0.76 volts, and we are going to obtain positive 1.50 volts. And that is the answer for that particular question. In the cell, the electrolyte is a paste. Explain. So as I've just said here, we have the electrolyte that is used. The electrolyte is a mixture of ammonium chloride and zinc chloride, and it's a paste. We're supposed to explain this. And this is because, or it is to provide mobile ions. Mobile ions. So ensure the ions they are free to move. This to provide mobile ions. To provide mobile ions. Part 3. What is the use of the zinc cap in the dry cell? As I've just said before, when you look at the structure of the leaf cleanse cell, the dry cell that you're talking about, we have the carbon rod, we have a section where we have a mixture of carbon, paste, and manganese oxide, and then we have a section where we have the paste, then we have the carbon rod, and then we have this carbon rod is the positive terminal, and then we have the zinc can that is all around the battery or the dry cell, but most of the times you find it at the bottom, which represents the negative terminal, and it is the zinc can that you are talking about. Zinc can, and it is the carbon rod. Carbon rod. So when you look at this particular cell, you notice that the zinc cap is used, or is the cathode, is the negative terminal of the cell. So we say is the cathode, or the negative terminal of the cell, negative terminal of the cell. So this is 1 mark. Let's now move to question number 21. State the functions of the concentric pipes labeled A, B, and C as shown in the brush palm. So this is a setup that is used during the extraction of sulfur from its deposits. And as we know, this process is done by use of 3 concentric pipes. The smallest, or the one with the smallest diameter, being the innermost pipe with 2 centimeter diameter, the medium pipe being 8 centimeters, and the widest pipe being 15 centimeters. So we know, according to what is presented to us at this point, this is the innermost pipe. This is the innermost. Then we have the middle pipe. Then we have the outermost. This is the outermost. The outermost pipe. So, as we know that the innermost pipe, through the innermost pipe, hot compressed air is passed through it. So we have at this point hot compressed air is passed through this pipe, and this particular hot compressed air is maintained at 15 atmospheres, a pressure of 15 atmospheres. And why do we maintain this high pressure? High pressure of this particular air is to ensure a light froth that consists of the mixture of molten sulfur and water is formed. A light froth is formed. And then through the outermost pipe, we have superheated water at around 107 degrees Celsius and a pressure of 10 atmospheres being passed through the outermost pipe. So here we have superheated water with a pressure, a temperature of around 107 degrees Celsius and 10 atmospheres pressure is passed through the outermost pipe. And this high temperature and pressure, the temperature ensures that there is melting of the sulfur deposits, or the sulfur mix. And again, the pressure is to ensure that the water remains in liquid form at that very high temperature. So water will not evaporate and become vapor at that particular moment. So the high temperature is to ensure that sulfur deposits or sulfur mix, and the high temperature of around 10 atmospheres is to ensure that water remains in liquid form at that very high temperature. Then through the middle pipe, we have molten sulfur coming through it. So we have molten sulfur that comes through the middle pipe. So we have molten sulfur coming through the middle pipe. So the method that we use here, we call it brush process, and it's based on the low melting point of sulfur, which ranges between 113 to 119 degrees Celsius. Let's now try to look at the questions down here. We are taught to state the function of A. We have said A is the innermost pipe. A, the innermost pipe, allows passage of hot compressed air. Allows passage of hot compressed air. B, which is now the middle pipe, allows passage of molten sulfur to the outside. Allows passage of molten sulfur. C is the outermost pipe, which allows passage of superheated water. Which allows passage of superheated water. So please learners to take note that if this question was to be brought in paper 2, a lot of questions will come out of this question. You'll be taught to state the conditions of hot compressed air. We have said that hot compressed air should be maintained at around 15 atmospheres pressure. The superheated water should be maintained at 170 degrees Celsius at a pressure of 10 atmospheres, and you're supposed to give reasons for the same. Let's now move to question number 22. The following chart shows a series of reactions. Use it to answer the questions that follow. Use it to answer the questions that follow. Looking at the flow chart, we can see carbon powder that is being passed through a chamber where carbon 2 oxide is. Then taken through step 1 where a colorless gas is formed and a brown solid is also formed. Then step 2 where a brown gas is formed and blue solution is formed. So we need to take note that carbon, in this case, the question comes from the topic carbon and its compound. And in this case, carbon is reacted with carbon 2 oxide, and we are looking at the reactivity series, whereby we know copper is below carbon in the reactivity series, meaning carbon is more reactive than copper. So carbon can displace the oxide of copper to form copper solid, and through that we produce carbon dioxide gas. So whatever is happening in the chamber where carbon 2 oxide is, carbon, which is a solid, is reacting with copper 2 oxide. And when they react, we produce copper, which is a brown solid, and carbon 4 oxide gas is released. And that is what is happening in step 1. After the brown solid is formed, taken to step 2, where a brown gas is formed and a blue solution is also formed. Whatever is happening here is that if you remember during preparation of nitrogen oxide gas, as we know that copper reacts with strong oxidizing agents and concentrated nitric 5 acid. When it reacts with concentrated nitric 5 acid, we do not form metal and nitrate gas as usual. Whenever copper reacts with concentrated nitric 5 acid, there is always formation of the solution of copper 2 nitrate, accompanied by water molecules, and the gas, which is brown in color, is always produced. And that gas is always nitrogen 4 oxide. We need to notice that whatever is happening here, we have copper solid reacting with nitric 5 acid, and we form copper 2 nitrate. Then we obtain nitrogen 4 oxide gas, and at the same time we obtain water. This nitrogen 4 oxide gas is brown in color, and the blue solution is copper 2 nitrate solution. So in this case, I can confidently say that brown gas is nitrogen 4 oxide gas, and blue solution is copper 2 nitrate solution. And that is what is happening in this particular flow chart. So starting with looking at the questions, we name the colorless gas. The colorless gas at this point, as I said before, is carbon dioxide, and the brown solid here is copper. Copper is a brown solid. Copper metal is a brown solid. So in this case, the colorless gas is carbon dioxide, and the brown gas is nitrogen. We are told to name. Kindly take note of the term name. We are not told to write the formula, we are told to name. So we are going to write nitrogen 4 oxide. Each have a mark. Each have a mark. Brown gas, sorry, we are looking at brown solid. Brown solid is supposed to be copper metal, and brown gas is supposed to be nitrogen oxide gas. Nitrogen oxide gas. Again, write the equation for the reaction in step 1 and step 2. As we have seen, in step 1, we have carbon reacting with copper 2 oxide. We have carbon solid reacting with copper 2 oxide solid. We obtain copper and carbon dioxide. We obtain copper metal solid and carbon dioxide gas. We balance by putting a 2 on copper 2 oxide and also by putting a 2 on copper. That is step 1. Kindly try to show step 1. That is for step 1. Then for step 2, we have copper formed solid reacting with concentrated nitric 5 acid, aqueous, and we obtain copper nitrate, copper 2 nitrate, which is aqueous, plus water, liquid, plus nitrogen oxide gas. We balance by putting a 4 on nitric 5 acid. We balance by putting a 2 on water and a 2 on nitrogen oxide. This is the equation for step 2, each 1 mark. Let's now move to question number 23. During solving process, how is carbon dioxide obtained? During solving process, how do we obtain carbon dioxide? Carbon dioxide during the solving process is obtained through the thermal decomposition of limestone or coke. So we say through thermal decomposition of limestone. Limestone is calcium carbonate, or thermal decomposition of coke. That gives you 1 mark. Part 2 of this question number 23. Give 2 reasons why the solving process is considered an efficient industrial process. Solving process is considered an efficient industrial process, and this because most of the raw materials are recycled. For example, we have ammonia and carbon dioxide being recycled. So we say this because most of the raw materials are recycled. For example, we have ammonia and carbon dioxide being recycled. Again, this gives you 1 mark. Give 2 uses of sodium carbonate. Remember, the main reason as to why we have solving process is to manufacture or to prepare sodium carbonate. So what is the purpose or the use of this sodium carbonate? Sodium carbonate can be used in softening of hard water. So we can say used in softening of hard water. We can also say in making of glass. Making of glass. So each have a mark, giving 2 score 1 mark. Let's now move to question number 24, which reads, aluminium is extracted from its ore by the electrolytic method. Use the diagram to answer the questions that follow. So as we can see, this is the setup that we use while extracting aluminium from its ore. Looking at it, we are being taught to name the above cell. Which name do we give to this type of cell? This cell, we call it R-root cell. The name of the cell is R-root cell or E-root cell. And why do we call it R cell? Most of the times you find it being called R cell. You still score the mark. Why do we call it R-root cell? Because it was discovered by 2 people. The first person was known as Charles Martineau, and the second person was Paul Arut. That's the reason the cell is known as R-root cell. The cell that is used during the extraction of aluminum metal. You need to understand this particular cell. This cell is made of several parts. It has the anode and the cathode, and in this case, we have carbon and carbon being used as both anode and cathode. So we have the carbon. These are the carbon anodes, which are the positive terminals. So these are the anodes. The anode, which is made of carbon, and we have again a thin layer of cathode, which is also made of carbon. So we have carbon cathode. This is the negative terminal. Again, we have the presence of molten ore that is now extracted. Where the aluminium is extracted, it is now the molten ore. And we also have the aluminium, molten aluminium being collected at the bottom. Molten aluminium. So looking at this question, As we know, during the extraction of this particular metal, there is the ore, we have chloride, what we call sodium aluminium chloride or chloride being added to the ore. Why is it added during the extraction or before the electrolysis? It is done to lower the melting point of aluminium oxide from around 2050 degrees Celsius to around 800 degrees Celsius. So we say to lower the melting point of aluminium oxide from 25, 15, 20 degrees, 2050 degrees Celsius or 2050 degrees Celsius to around 800 degrees Celsius. So you can simply say to lower the melting point of aluminium oxide, and that will still give you 1 mark. Write the equation for the reaction that produces aluminium at electrode B. Electrode B, as I had said, it is the cathode. Electrode B is the cathode. So we are writing the equation at the cathode. So the equation at the cathode, as we know, aluminium ions are discharged at that particular electron. So in this case, we write aluminium ions aqueous gaining electrons, if you don't know, and we obtain aluminium solid. You need to understand that this is a reaction at the cathode. Whenever you are writing these equations, we have to consider the two sides, the anode and the cathode. And we always start by writing the reaction at the anode, so that we know the number of electrons that has been lost, they are the same number of electrons that has been gained. So I will try to do my rough work somewhere and try to see how to balance this particular equation. So in this case, we have on the other side, we had at the anode. At the anode, we had oxygen ions, which discharged electrons to produce oxygen molecule, which is gas, and electrons. So when I look at this, I'm going to come up with least multiple factor, or in other words LCM. So in this case, I balance here by looking at, if I try to balance here, I will have 2 electrons, and on the other side I will have 3 electrons here on aluminium. So what we always do, we look for the LCM of these 2. That is, we're going to have aluminium and oxygen. So I balance the aluminium. I want to make it 12 electrons. So I'll multiply for the anode, I will have 6, because those will be 12 electrons that has been discharged, and for the oxygen it will be 3. So that now we have 6 oxygens. Then as I try to balance for the electrons in aluminium, I make them 12, so I multiply by 4, and I multiply this by 12, and then the aluminium here will also be 4. So you realize that I've used 4 and 6, the LCM or the least multiple factor I've used 12. So in this case, I'm having the reaction at the cathode. So this is the reaction at the cathode, and this is what is being marked. This is just a summary or a rough work to show how we obtained the balanced equation. Let's move to part D of this question. Explain why electrode E has to be replaced periodically. Electrode E, we have said, is made of carbon, and as we know, carbon, there is oxygen, because remember this is the anode. So anode, this discharge now, we're going to have oxygen being preferentially discharged at the anode. So this carbon will always be reacting with oxygen. The carbon reacts with oxygen to produce carbon dioxide, and therefore it gets wearing out. That means it must be replaced. So we say it's made of graphite carbon which reacts with oxygen to form carbon dioxide. So we say it's made of graphite. It's made of graphite, which is carbon, which reacts with oxygen discharged at the anode with oxygen to form carbon dioxide. So it forms carbon dioxide, it means it wears out, and therefore it has to be replaced periodically. So that gives you 1 mark. Let's move to the next question of this paper. The setup below was used to prepare and collect hydrogen gas. As we know, learners, hydrogen gas, we learned in Form 1 what an hydrogen, and we notice that whenever we want to prepare hydrogen gas, we have to react a metal and an acid. And the most appropriate acid that we used was HCl, diluted hydrochloric acid, and zinc metal. But we also have another method, other ways of producing hydrogen gas. By reacting water and hydrogen and a metal, we always produce an hydroxide, and hydrogen gas is produced. So we write an equation for the reaction. In this case, we are reacting water and calcium. The reactivity of metals with water, that's what we are looking at in this question. So we write an equation for the reaction that produces hydrogen gas. So the reaction here, we are reacting calcium and water. So we are reacting calcium solid plus water, which is liquid, and we obtain calcium hydroxide. Considering the valencies, we have 2, and this is an aqueous solution, and we obtain hydrogen gas as well. So we balance the equation by putting a 2 on water, and the equation balances out. So this gives you 1 mark. So in another time you are reacting a metal and water, you always produce a metal hydroxide and hydrogen gas. Explain why hydrogen gas is collected over water. The reason as well we collect this gas over water is because the gas is slightly soluble in water. We don't say the gas is insoluble in water, we say the gas is slightly soluble in water whenever we see the gas being collected over water. So we say it is slightly soluble in water because it is slightly soluble in water. The gas is slightly soluble in water. This gives you 1 mark. Moving to the next question, number 26. Use the information in the table below to answer the questions that follow. Use the information in the table below to answer the questions that follow. The letters do not represent the actual symbols of the elements. So we have element B, C, D, E, and F. The atomic number 18, 5, 3, 5, and 20 respectively. We have 18 as the atomic number, and so another interpretation of atomic number is the number of protons. And we also need to understand what we learned in the structure of an atom. The number of protons is always equal to the number of electrons. So we also have mass number. Mass number is given by the number of protons plus the number of neutrons. So these atomic numbers represents number of protons, can also represent the number of electrons. So looking at whatever we are given, we are told that which two letters represents the same element. Give a reason. Give a reason. We have atomic number 18, mass number 40, atomic number 5, mass number 10, atomic number 3, mass number 7, 5, 11, 20, 40. You notice that we have atomic number that has repeated itself. That's where we get what we call isotopes. What are isotopes? Isotopes are elements, atoms of the same element are atoms of the same element, atoms of the same element with same atomic number but different mass numbers. So these are what we call isotopes. For instance, I can have carbon 14 and carbon 12. These are different atoms, different atoms of the same element. So in this case, when you look at these, you realize that the atomic number are the same for C and E, but the mass numbers are different. So these are isotopes. So we are told which two letters represent the same element. Give a reason. So we say C and E. C and E. Reason? They have same number of protons. They have same number of protons. Same number of protons, or they have same atomic number. So stating 1 mark correctly and giving a result 1 mark. Give the number of neutrons in an atom of D. Atom of D. Neutrons, we are going to get it from the mass number, whereby we know mass number is given by the number of protons plus the number of neutrons. So we already have the mass number, which is 7, is equals to protons, atomic number 3 plus neutrons, which we are doing not know. So mathematically, we are going to have n is equals to 7 minus 3, and our number of neutrons equals to 4, and that is 1 mark. Moving to the next question, number 27. Use the table below to answer the questions that follow. Solution A, B, C, D, and E. We are having different pH values. A with a value of 1, B 7, 6, C 6, D 10, and E 10. We know we have what we call the pH chart or pH scale, which runs from 0 to 14. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So from 0 to around 4, those are strong acids. Strong acids. Then from 5 to 6, those are weak acids. Then 7 represents neutral. Then we have 8 to 10, those are weak bases. Then we have 11 to 14. Those are strong bases. So that is a pH scale. And we know examples of these particular different groups of acids and bases. Identify a solution that is likely to be wood ash. Wood ash is a base and it's always a weak base. So a weak base will range between, I've said weak bases range between 8 to 10. So in this case, D will represent a weak base. So in this case, D will represent a weak base. This is a weak base. Citric acid. Citric acid is an acid, but it is a weak acid. So it ranges between 0 to, that's not 0 to, we have between 5 to 6. 5 to 6. So in our case here, we have 6. So we have each one mark. Give an example of a solution that is likely to have a pH value of 7. So neutral solutions are from, most of the times, from normal salts, like in case of sodium chloride solution. So an example is sodium chloride solution. And or any other normal salt solution, dissoluble sodium chloride solution. Name two uses of acids. So here you have to give specific examples of acids as you give the function. So here we are going to have sulfuric 6 acid is used in car batteries. Sulfuric acid is used in car batteries. We also have vinegar used as a food additive. Vinegar is used as a food additive. We may add more other uses, like hydrochloric acid is used in digestion in the stomach. So 81 mark. Let's now move to question number 28. Question number 28. Use dot and cross diagrams to show bonding in the following compounds. We have sodium chloride. As you know, it is a compound that is formed by use of ionic bonds. Ionic bond. This between a metal and a non-metal. And as we know, we need to understand that for sodium, it's going to lose one electron, and for chlorine, it's going to gain one electron. So we are just going to go directly to the final representation of that particular bond. So we are going to start with sodium. Then we are going to put 2 energy levels. So we are going to use process, 2 electrons, 8 electrons, because it has lost the 1 electron, because it always have 11 electrons. Then we use these square brackets, and then we put a plus sign to show that it lost 1 electron. That is for sodium ion. And then for chlorine, that is chlorine. Chlorine is 287 and it's going to gain 1, so we are going to have 3 energy levels. So we have the first one, the second one, and then we have the third one. So we have we are going to use dots. So 2, 8, then we have 7, 7 dots, and then the one cross that has been lost from sodium, and then we enclose with square brackets, and we put a negative sign to show that chlorine gained only 1 electron, and this was to give you only 1 mark. For ammonium ion, as you can see, is a type of bond that we call a dative bond, where electrons from one of the ions to one of the ions, the electrons that bonds nitrogen to one of the hydrogen is datively bonded, and because nitrogen fully contributes the paired or the shared electrons. So in this case, I'm going to have basically supposed to appear, if I can use the Lewis structure, it's supposed to appear this way. And then we have the dative bond, and then I close this way with a positive. But now, because I'm supposed to use cross and dot diagrams, I'm going to have nitrogen in the middle, nitrogen in the middle, then I'm going to have 4 hydrogens. 1, 2, 3, and rectify this. 3, 4. So in this case, these are hydrogens. These are hydrogens. So 3 hydrogens supposed to be hydrogen supposed to be here. Hydrogen, 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 hydrogen. So 3 of the hydrogens are covalently bonded. So we are going to have cross dot, cross dot, cross dot. So to balance the hydrogens are already balanced. We don't need extra number of electrons. So hydrogen only need to gain 1 electron to be stable. Then, because now we have the dative bond, we have one that is datively bonded with nitrogen. So the lone pair of electrons in nitrogen, they are shared with the remaining nitrogen, and that is how the dative bond is formed. And because we have this, we also have to enclose with a positive sign at that point there. So this again gives you 1 mark. Please don't use the Lewis structure when you are not directed to use. Use only when you are told to use. So in our case, we have to use cross or dot diagram. We are supposed to use cross or dot diagram. So that is how we were supposed to do it. Let's now move to question number 29. The diagram below shows preparation of oxygen gas. This is one of the methods that we use to prepare oxygen gas in the laboratory by reacting hydrogen peroxide in presence of a catalyst that we call manganese oxide. We also use other methods like reacting sodium peroxide with water. And we also have decomposition of potassium nitrate. It's another method that we can use to prepare oxygen. But in our case here, we are using decomposing hydrogen peroxide in presence of manganese oxide. The first question is complete the diagram to show how dry oxygen can be collected. So in our case here, we want to collect dry oxygen gas. So in my case, I'm going to have to first connect my gas delivery tube to a U tube packed with anhydrous calcium chloride. This is to ensure the gas is dried before it is collected. So in my case here, I'm going to have the setup looking like this. Then I cork. Then of course I'm going to pack with anhydrous calcium chloride. So this is anhydrous calcium chloride. Then after packing the U-tube with anhydrous calcium chloride, I can then collect my gas by use of a syringe. So in my case, I'm going to have a syringe that looks like this. I'm going to use my syringe like that. Then I ensure that it is well corked. So I label. It is a syringe. It is a delivery tube. Yes. So through that, and this is oxygen gas. Oxygen gas. So that is how we do it for 2 months. That is drawing correctly 1 mark, workability 1 mark, and labeling. We have a mark for drawing the U-tube with the correct drying agent, and then that is half mark. And then we also have use of the correct use of best method for gas collection, have a mark, and workability 1 mark, total 2 marks. We use these methods when you're not sure of the method of collection. Most of you find using downward delivery. Remember, oxygen is less dense than air, so we don't expect you to use downward delivery. So when you're not sure the method that you're supposed to use, just use syringe and you score the total mass. What is the importance of the high percentage of nitrogen in air? Why do you think that nitrogen is important in the air, in the atmosphere? So one of the reasons as to why this high composition of nitrogen, 78%, is to help to dilute oxygen that reduces the rate of combustion. So we say helps to dilute oxygen, reducing the rate of combustion, and also prevents materials from burning easily, Remember, oxygen is the gas that supports combustion. So if there was only high amounts of oxygen in the atmosphere, then combustion could be very easy to occur. That's the reason nitrogen is there to dilute and to reduce the rate of reaction whenever oxygen tries to cause combustion. So again, 1 mark for that explanation. So this marks the end of our presentation. If you found this presentation useful to you and you have not subscribed to our YouTube channel, Shining Crates Online School, we request you to do so that you'll be updated whenever we post a video that is of this kind. Still, if this video was useful to you, share it to your friends comment your reactions as we prepare to upload more videos of this kind. Thank you for watching, and may God bless you abundantly. Thank you. Welcome again.